So, hello everyone. This week we will discuss the solutions to previous year's assignment 4. So, hopefully you are able to see all the notes in the Google Drive link, I believe. So, for those of you who do not have the Google Drive link, I will provide the link right now. So this is the Google Drive link where we have all the lecture notes from all the previous sessions and the previous year's assignment solutions. So if I remember correctly, I had not discussed assignment 2 solutions in a video lecture, but I had uploaded the solutions in the form of a PDF in the Google Drive. So I believe you would have gone through those solutions and I believe you would have understood the concepts. If not, then you can put it up in the forum. So this is the Google Drive where we upload all the lecture notes. Then there is the YouTube channel. So I'll provide that link for those of you who do not have it. So this is the YouTube link for those of you who do not have the link. So this is the Google Drive and YouTube link. These are the two links that you should save and bookmark, and you should subscribe so that you come to know about each of these sessions that we have. So for today, we will focus on assignment 4. So this is a fairly simple assignment, so to say, and we will start by solving the questions, and this will help you in solving the current assignment 4. So the first question says that we have a labeled classification data set which has 10 features and 500 observations from 5 different classes. Then the number of minimum possible dimensions in which the data set can be reduced by using LDA, the linear discriminant analysis, is, we need to select one of these options, and the correct option is 4. Why? Because if we have C number of classes, then with LDA we can go to C minus 1 dimension. So in the reduction you would have C minus 1 classes. So we have 5 classes over here, so 5 minus 1 is 4. And before proceeding, I would like to list down some features of both the PCA, the principal component analysis, and the LDA, the linear discriminant analysis. So let me write down some properties. This will help you in solving the subsequent questions as well. So PCA for short, and then we have the linear discriminant analysis, which is LDA. Okay, so some properties we will write. So for PCA, it is for feature classification. And LDA is for data classification. PCA can be thought of as a form of unsupervised learning. More details will come up in the upcoming lectures, but for now you can just take these terms. So hopefully you people have watched some of the lectures from week 4. If not, it will be difficult to understand today's assignment. And in PCA, we project the data in the direction of maximum variance. So where there is maximum variation or maximum variance, we project our data in that direction. For LDA, we project the data in the direction of maximum separability. So it should be maximally separable, and this separability is between the classes. And PCA can be used to reduce data to any lower dimension, So whatever dimension we have, let's say here we had 10 dimensions. So 10 dimensions can be reduced to 8 dimensions, 5 dimensions, 2 dimensions. But in LDA, we can reduce data to number of classes minus 1, this dimension. So we saw 5 classes can be reduced to 4. So this is like some basic features and properties between PCA and LDA. Next question is that we are given a 2D data with 5 samples, and these are the samples that we are given. And then we need to find which of the following matrices is the possible covariance matrix for this data set. So first what we will do is we will shift our data by the mean. So we have the means as for x, the mean will be 1 plus 2 plus 3, summing up all the data points and dividing by the total number of points. So this comes out to be 3 along the y column. This comes out to be 6. So now we can shift our data by these means. So shifted data comes out to be, we will have x and y. So x, first element is 1, and then we'll subtract 3. 3 is the mean. 2 minus 3, 3 minus 3, and 5 minus 3. Then we have y. For y, the mean is 6. So 2 minus 6, 8 minus 6, 6 minus 6, 4 minus 6, and 10 minus 6. So this is, let us just write it down again, the actual values. So 1 minus 3, that means negative 2, then negative 1, 0, 1, 2, negative 4, 2, 0, negative 2, and 4. So this is the data which is shifted by the mean. And then the data matrix. So we form the data matrix C, which is simply this matrix right here. So we call it the data matrix C. So that is negative 2, negative 4, negative 1, 2, 0, 0, 1, negative 2, 2, and 4. So this is the data matrix, which is a 5 cross 2 matrix. So, and the covariance matrix is given as follows for this data matrix. So some people write 1 over n, some people write 1 over n minus 1. Technically speaking, 1 over n minus 1 is more correct than 1 over n. So ideally, this one is more precise, so to say. You can use 1 over n. So if your n is very large, then 1 over n or 1 over n minus 1 would not make much of a difference. But when your n is small, strictly speaking, you should be using 1 over n minus 1. So yeah, so some people use 1 over n or 1 over n minus 1, but you should be using 1 over n minus 1, especially when the number of elements, when n is small. So this is the definition of the covariance matrix. So we can just find it out. So 1 over n is 5 in our case, 5 minus 1. C transpose. So this is C. The C transpose would be switching the rows and columns. So rows become columns, columns become rows. Let me write it down a little bit over here. Sigma C is 1 over 5 minus 1. Then C transpose, -2, -1, 0, 1, 2. This is C transpose and then C. So now simply we need to multiply. So the prefactor is 1 over 4 and then -2 into -2 plus -1 into -1 plus 0 plus 1 into 1 plus 2 into 2. That gives me 10. Then this row, first row over here, second column here, you would get 12. Then second row, first column, that gives you 12 again. And second row, second column gives you 40. So this is the covariance matrix, which is symmetric as it should be. So which one is the correct option out here? So D is the correct option. So moving ahead, we have the next question. So this question is, if the direction of the principal component of a data set in PCA is given by this vector, then in 2D to 1D reduction, the point 1, 2 maps to which of these numbers? So what we have is, we are given a point which is x. X is 1, 2 vector. And then we are given a vector v. And then we need to find out the mapping of this point along this vector in the PCA. So how that is given? So mapping or projection, you can call it mapping or projection, either one, is simply V transpose times X. So what is V trans? This is V. So V transpose would be 2 over root 5, 1 over root 5, and X is 1, 2. So pretty simple. 2 over root 5 times 1 plus 1 over root 5 times 2, which is nothing but 4 over root 5. So option number D again. Now we have some question based on the properties of PCA. So which of the following statements are true about PCA, the principal component analysis? First statement they have given is that the covariance matrix in PCA is always symmetric. Next statement they have given is that the eigenvector corresponding to the smallest positive eigenvalue is the first principal component. Then they have written that PCA is primarily used for the task of dimensionality reduction. And the fourth statement that they have given is that the covariance matrix in PCA is not a positive semi-definite matrix. So these are the four statements they are given. They have given over here, and we need to select which of these statements are true. So clearly the first statement is true because covariance matrix is, or by definition of a covariance matrix, it is symmetric. The second statement is false because eigenvector corresponding to not the smallest positive but the largest positive we take. So this is false. We take largest eigenvalue instead of smallest eigenvalue. And what does that denote? So largest eigenvalue, the eigenvector corresponding to the largest eigenvalue gives us the direction of greatest variance, greatest variation that is possible. That is the significance of the largest eigenvalue, which will not be for smallest. Smallest would be least variation. So second statement is false. And similarly, fourth statement is also false. The covariance matrix is not a positive semi-definite matrix. This is also false. So the only true statements are statement 1 and statement 3. PCA is primarily used for the task of dimensionality reduction. This is true. So the option is C, correct option. Statement 1 and statement 3 are the correct statements. Next, similar type of question we have, but this time for LDA. So the question says, which of the following statements are not true about LDA? So this time we need to find out which are not true about LDA. So first statement says LDA performs features classification. Next statement is LDA is an unsupervised machine learning technique. Then third statement is LDA projects the data in the direction of maximum variance. And the last one is LDA is a supervised machine learning technique. Now this statement, the fourth statement, is the only true statement out of all these four. So that means 1, 2 and 3 are not true. So the correct option is A. 1, 2 and 3 are not true. And just to remind you, we will go up over here. So this was features about LDA. So we'll go up. I had written down the features of LDA and PC over here. So we see that LDA is for data classification. LDA is a supervised learning technique. LDA projects the data in the direction of maximum separability between the classes and reduction of the data by one dimension less. Whereas for PCA, we have feature classification. PCA is for feature classification. It is an unsupervised learning technique. It projects the data in the direction of maximum variance and it reduces data to any lower dimension. So we see that all the first three properties over here, features classification, this is not true. This is true for PCA. PCA does features classification. PCA does feature classification. Then LDA is an unsupervised machine learning technique. Again, this is wrong. PCA is unsupervised machine learning technique. So this is also for PCA. And third statement, projection of the data in maximum direction of variance. So that is also for PCA. Projects data in direction of maximum variance. So all these first three statements are indeed true, but they are true for PCA, not for LDA. For LDA, only the fourth statement is true. So moving ahead. Now we have some questions based on syntax of using Python for PCA and LDA. So the question says, while implementing PCA in Python, what does n indicate in the function PCA n components equal to n? So the options are dimension of the given data set, dimension in which the data set has to be reduced, a fixed value of 1, and number of classes in the data set. So the correct option is dimension in which the data set is to be reduced. So let me write down the syntax for you, the syntax that you would use for PCA. So what you would do is you would import from the sklearn package So you would import PCA from the sklearn.decomposition package in Python. And to use this PCA then, you would have the following syntax. And then you would use PCA.fit to the data. And then finally, you will get the transformed vector by using PCA.transform. Now, let me just write down what these terms mean. So, X is the data that we have. N is the dimension to which we need to reduce. So, this is for the reduced dimension. And this XP is the transformed data. And this transformation is done by PCA. So this is a syntax, simple 3-4 lines you need to use in order to do PCA in Python. Next, we have another Python question for implementing LDA. So the question is, which of the following is correct for applying LDA considering the sklearn utility in Python for defining machine learning models? So we have these 4 options for using sklearn for performing LDA. The correct option is option number, sorry, I used the wrong color. The correct option is option number B, which is from sklearn.discriminant analysis, import linear discriminant analysis. Now, again, I will write down the syntax for you, the syntax for using this in Python. So for this time, you would do sklearn.discriminant you would import the linear discriminant analysis. Then you would say LDA is equal to linear discriminant analysis. Then you would invoke LDA.fit to use LDA. And then you can plot it. So you can plot it. Now over here, let me write down what these terms mean. So you have X is data, Y is the classes. So your data will be divided into various kinds of classes. So Y gives you the information about the classes. So if you have 10 data points, let's say 3 belong to one class, 3 belong to another class, and 4 belong to the third class. Then that information would be there in this vector Y, which tells which elements are belonging to which class. And then finally, this is you have the transformed data. By LDA. So this is the simple, again, some 3-4 lines of code that you would use to perform LDA in Python. So next, so this is quite a short assignment, by the way. So you would be able to solve it pretty much easily. So what is the use of matplotlib library in Python? For plotting graphs, for working with arrays, for adding numbers, for developing machine learning estimators. So by now everyone would have used matplotlib, and it is for plotting graphs. There's another package which is used for plotting. People sometimes use Seaborn. So Seaborn is also used for plotting graphs. Working with arrays, you all know it is NumPy. And then adding numbers. Adding numbers is pretty much simple. You just do 2 plus 3 and then you would get answer as 5. It's as simple as that. And for machine learning, you are in these lectures, you have seen that you are using sklearn for the machine learning estimators that you have. So these are the uses of these packages. So matplotlib is used for plotting graphs, and you can also do so matplotlib plotting graphs. You can also and graphs means you have 2D 3D both functionality, both 2D and 3D, and it is also used for making animations. So again, 2D 3D animations you can make in matplotlib. So not just graphs are like just static visuals that you would have. So not just static visuals, you can also have dynamic visuals, which are animations with the help of matplotlib library. You can check out animations in matplotlib. So simple code is there, you can use that for making animations. Then the next question that we have is that we are given a covariance matrix of a 2D data set having features given as f1 and f2. Then the correlation between the features in f1 and f2 is what we need to find out. So let us solve it. So we have a 2D data set. So f1, f2 are the features of the 2D data set, and the correlation between the features is given as follows. What is the sigma 1, sigma 2? Let sigma 1, 2, sigma 1, 1. So this is the elements of the covariance matrix. So you have the covariance matrix. So, and because it is symmetric, covariance matrix is symmetric. So sigma 1, 2 is same thing as sigma 2, 1. So you can plug in these values. So you are given this covariance matrix right here. So from there you plug in the values. Sigma 1, 2 is nothing but 0.9. And sigma 1, 1 and sigma 2, 2 are 1, both of them. So this is 0.9. And now we come to the last question. So again, it is based on the last video of this week 4. So you can see week 4, lecture 4 and 5. So suppose SW and SB are within class and between class scatter matrices respectively. Then in LDA, we need to maximize this JV expression. So JV is what? JV is this big expression right here, V transpose SBV over V transpose SWV. Then V is given by, so this is given by the eigenvector of SW inverse SB corresponding, and then you need to select the largest eigenvalue of that, and corresponding to that eigenvalue, the eigenvector that is there is what is going to be your V. So it is a lot of maths is there, like simple maths, but a lot of algebraic steps are there to arrive at this conclusion, and this is given in this lecture. So if you have not seen the lecture, you can go and watch this lecture. So lecture 4 is where the maths is there, and lecture 5 is for the Python thing. So how to implement it in Python. And sorry, this is week 4, lecture 4, 5. So week, which week? Week 4. So it is there in this, so you can go and watch this lecture. It would be difficult to explain this right now. So if you have not seen that lecture, please go and watch week 4, lecture 4, and you would understand it. It's just straightforward maths, just a lot of steps are there. So yeah, this is all for this assignment. It's a pretty short assignment. And why so? Because you have already learned the basic mathematics of eigenvalues and eigenvectors and matrices and basics of linear algebra in the previous weeks, in the previous 3 weeks. So this is week 4 that we are running right now. So in week 1, week 2, week 3, You have already learned all the basics that you would have to learn for this week at least. In the subsequent coming weeks, you would learn a little bit more mathematical techniques. But for now, this was the basic mathematics that you needed in order to apply some of these concepts. So this week has primarily focused on implementing them in Python. So you have two lectures in this week wherein you see how things are implemented in Python, what kind of code you would write to run both the PCA, the principal component analysis, and the LDA, the linear discriminant analysis. So it is one thing to know the maths, it is good to know the maths, and after knowing the maths, you need to apply it also. So those lectures, so Python lectures are basically, and there are two lectures in week 4. So week 4, lecture 3 and lecture 5, both of them are for Python implementation. So you can go through those lectures and write down the Python code simultaneously side by side in the lectures, and then you would be able to follow it. It's pretty much simple, nothing so much complicated. Let me see something going on in the chat. Does our exam only have MCQ or derivations are also asked? So Akhila, your assignments will be MCQ based only. I'm not sure about the mid-sem exam and the EdSem exam. I will confirm that in the next class. But all your assignments will only be MCQs. You would not have any derivations. Derivations are only there for your understanding, and so that you understand the maths behind it and the steps behind every thing that you are applying. Deepak Ahire has something X transpose V as well. Which question is that supposed to be for? I forgot. Let me go up. I think for this question you want to say. This question number 3 you want to say, Deepak, right? So what you want to say, you want to write this as what? Let me see what you have written in the chat box. You have written X transpose V. So you want to write this as X transpose V. So yeah, if you write it as X transpose V, then you have this, and then your V is. So this is pretty much simple because it is 2D to 1D projection. So this is the same thing. So you have 1, 2 and 2, 1. So this is the same thing. You would get 4 over root 5. But typically, what you want is you want to project your X into the direction V. So this kind of feels as if I'm projecting my V in the direction of X. So now if you think of simple dot product in 2 dimensions or something. So if you have 2 vectors, so you're taking dot product of first vector with the second vector, same thing as second vector with the first vector. But this might not be the case when you have lots of dimensions and you are trying to reduce your dimensions from 10 dimensions to 7 dimensions or something. So typically you should try, and so mathematically or logically speaking, it is like you're projecting your X in the direction of V. So with that logic, you should be focusing on this definition rather than the other definition. So yeah, but it's the same thing over here. Just like I said, so in 2D you have 2 vectors. A dot B is same thing as B dot A. But things might not be this simple for higher dimensions when you have dealing with different dimensions. So yeah. So that's all for today. It was pretty much a short assignment because, as I said, so this week is primarily focused on implementing these things in Python, and you have simple implementation, means the maths might look complicated, but Python has done all that maths behind for you. So you see that you have just 4 lines to write in order to get your PCA. Similarly, 4 lines in order to get your LDA. But in order to understand as to exactly what is happening behind it, for that the maths is there. For that those theory lectures are there which explain as to what is happening, so that when you have some application in mind, you know whether you want to use PCA or whether you want to use LDA. So you should have that clarity in mind. And in order to have that clarity in mind, you need to understand the mathematics behind it. So this is the aim of this course, so to say. So yeah, any other question? So could someone just tell me if you have been able to access week 2 assignment questions? Since I did not discuss it in a video, I just uploaded it on the Google Drive. So can someone just tell me that they have been able to access the assignment 2 solutions? Okay, Deepak says yes. So I hope people have gone through that and people are able to understand that. Do you want me to? Yeah, Akhila says yes. So I don't think you want me, or do you want me to do that in some lecture, like make some video out of it? Or are you happy with the lecture notes? Someone can just say, maybe write that they are happy with the lecture notes, or whether they want the video lecture for that as well. Okay, fine. I think it's fine. So I will get back to you regarding the question format. Happy with the PDF. Okay, fine. So I will get back to you with the question format for the mid-sem and end-sem exam. I'm not sure whether that is also going to be fully MCQ based or some descriptive questions would be there or not. So I will confirm that once with the other TAs and the instructors, and then I will get back to you regarding this. But all your assignments are definitely going to be only MCQs. So yeah, that's all for today. And for those of you who joined late, I will provide the links to you once again. So these are the links for the Google Drive where we upload all the lecture notes. Please refer where we can see derivation of PCA in detail. Okay, I will tell that. So this is in week 4. Week 4, lecture 1 and 2 are for PCA. So I think I do have some notes. Like I also watch the video lectures like you, and I also prepare some notes just to know what are there. So if you want, so these are like my notes that I have prepared from the lectures. So as you would have seen, instructors upload some lecture notes below the video, their PPT slides and those notes that they create in the lectures, they upload that over there. But I also watch the videos and I also prepare some notes. So these are my notes. So PCA you want to know, so this is lecture 1 is for PCA, and then lecture 2 is also for PCA. A more in-depth derivation of PCA is there in lecture 2, and then in lecture 3 you have the Python implementation. So Jatin, you can watch video lectures 1 and 2 of week 4. So since I have these lecture notes, like, do people want my lecture? These are very brief notes, by the way, because I am only writing in very concise, whatever basic stuff, not in detail, because I am aware of these mathematics. So I only write some basic stuff, maybe here and there, stuff which I feel is necessary to write. So do people want my lecture notes? Or if you want, I can upload that also on the Google Drive. So if most of you say that you want, then I can do it. So Pooja is saying, can we have your notes as well? Jatin also, please share your notes also. Think Lagrange multiplier was not. Okay, fine. Seems like most of you want my lecture notes. So I have also lecture notes. I will upload. So these are mostly concise lecture notes, by the way. So it will maybe help you revise your concepts before your final exam. So I will upload these lecture notes as well. Someone is saying, in this formula, how did we write phi? Which phi are you asking about? Are you asking from these lecture notes, or are you asking from some assignment? I'm not sure which formula is this. Expectation of the error. Okay, so in this derivation, somewhere over here you are asking. Yeah, okay. Oh, how do we write this? Okay, fine, fine. So this is, you see, these are like two summations, okay? So mathematically speaking, you would not want to use same index of summation for both the summations. So so yeah, this is a square, right? So this expression, I think I wrote a little bit wrong over here. I will correct it. One of these guys should be a transpose. Anyway, so this thing that you have over here, it's a square, and it is a, first you are doing the summation of this guy right here, and then you are taking the square. So this is just being expanded into, like, you are opening up the square, and then you are using different indices for the different summations. So I and j summation is there coming from that, and that's why you have these I and j indices, and then you would have I and j indices are there. So, and this term right here would give you a Kronecker delta function. So from that is there. If you want, I will write down a little bit more details over here. I will put in little bit, maybe one or two more steps. Let me write down over here. So I need to upload my notes, and I will put in some more steps. Sorry? Yeah. Yeah. Okay, so that part you are trying to ask as to why this thing is there. Okay. Yeah, that's a good point. So I typically would write, when, see, typically when you are having a square of something, then you would, it's like a modulus square of this error that we have defined. So you want this error should be a number, right? So if you just do, this error should be like some number between 0 to 1 if it is scaled. uh like lesser number of error, zero error meaning it is perfect, and error being one meaning it is completely imperfect. So if you just write, this is just intuitive way of trying to explain things. So if you just write phi I phi j, first of all, this matrix multiplication itself would not be defined, and this would not give you a number. So in order to get some number kind of stuff, you need this error to be a number, not some matrix or scalar or vector or something. So you would want it to be a number. Now just doing phi I phi j, or phi I, so to say, if we just want to keep same indices, just doing this or just doing this is not going to help you to get a number. To get a number, you would need to use this particular combination of phi I transpose phi I, but I would write it down a little bit better over here in this margin. Maybe I would write this. So basically the crux is from this step. So I would just write it down maybe a little bit better over here before I upload this lecture notes. So before I upload it, I would put that thing over here a little bit better as to why this phi transpose is there. But intuitively you can think that error needs to be a number, and how you would get a number from vectors. Yes, yes. Yeah. So I have missed out some transpose out here. So all of one of these terms is definitely transpose. So this is a square, right? You have a square. You would open it up as a transpose times this, like this. So yeah, I need to put some transpose in one of the whole terms. So you, when you open up a square, you do transpose and then the same thing. So I guess this guy, so I've put transpose over the I. So this guy right here would then be the transpose. So there's some mistake over here. So this whole thing over here is a transpose. then this transpose. So, and then when you change the indices, when you separate out the indices for the summation, you have I for 1, J for 1. So I transpose and J. So that's way. So this is the thing. You open up the square into transpose times the thing itself. Ma'am, please include part of Lagrange multiplier step for minimizing with given constraint in notes. So exactly where you want this thing? Oh, over here, this Lagrange multiplier. So Jatin, is this your query? So exactly what is your query? See, if Lagrange multipliers is your query, then let me tell you one thing. So Lagrange multipliers is a technique. It's a very fantastic technique and it works like magic. So it's a very fantastic technique used for any minimization, maximization of any such kind of problems. Now, what we are doing over here is, so we were to minimize our error that is given over here, this big expression over here. So this is the expression for our error and we want to minimize this error. Now what we know is that we are given this constraint of normalization. So this constraint is basically that everything is normalized. So now what is happening is this term, if you look at it, is essentially 0. This term is not contributing anything. Why? Because phi I transpose phi I is equal to 1. So 1 minus phi I transpose phi I, so that is 1 minus 1 and that is 0. Okay, so this is your error. This phi I transpose sigma phi I. So this term right here, let me highlight it maybe. So this term right here is your error term. This error. And to that you are adding something which is 0. So you can always add 0 to anything, right? Error plus 0 is same thing as error. Now, the reason why we are doing is this, that we know that we have some constraint on this phi I. And this is the kind of constraint, the normalization constraint. Now you can definitely add 0 times something. So this is like adding 0 times a lambda. But this lambda is now a variable and it is giving you some control over maintaining this constraint as well as minimizing your error. So essentially this step right here, so this step and this step is the same thing. Not much, there is nothing really different, and the magic happens because of this lambda I. So this lambda I is really like a magical thing. So it's like you are adding 0, but still you are able to solve the question. So this is the beauty of Lagrange multipliers, and you would use it typically in any kind of minimization questions where you have some constraints. So you have some constraints. So here this thing is equal to 1. Had you, if you would have had some constraint where you have some condition is equal to 0, is equal to let's say 5, then you would do 5 minus that constraint over here times lambda. Understood. But should summation part be there in second term? Yes, of course, because we are trying to ignore all the terms beyond a certain value, I equal to m plus 1 up until n. So we are trying to take some part of the data that we have and trying to ignore beyond that part. So this is kind of like approximating it and deleting some part of the data. So again, you are summing over 0. So you add 0 10 times or you add 0 100 times, it doesn't make any difference. But you want to be consistent. So here you are going from I equal to m plus 1 to n. You want to be consistent. You want to use the same kind of structure for the first term as well as the second term. Because you are deleting certain eigenvalues, or you're deleting some part of the data. So that same part you need to be consistent throughout in both the terms. So yeah, that is it. So I'll upload these notes, and since you people want, I will upload it and I will try to proofread also a little bit. So when I was taking it for myself, I was not paying much attention, but now I think I need to put in some attention. So I will proofread these notes for you before uploading it. So yeah, you can have these lecture notes also. There is nothing personal about these notes. It's from the same videos that you are watching, same videos even I'm watching. So yeah, that is about it. So this was for assignment 4. Uh yeah, if you want PCA, you watch lecture 1 and 2. If you want LDA, then you watch lecture 4. So yeah, that's about it. So thank you. And for those of you who don't know, this is the sorry, I think I sent it personal to someone. So I'll send this to everyone. So this is the Google Drive where I will upload all these lecture notes as well as these assignment notes. And this is, I'll give you the YouTube link. So if you miss something, if you miss some session, if you're absent someday, no worries. You can always go to the YouTube channel and watch the video. Okay, then that's all for today. So thank you everyone. We'll meet next Saturday. Yeah, thank you.
Recording stopped.